Welcome to the week 4 of a Calculus 2 class. This week we will learn new integration technique called integration using partial fractions. Often when working with partial fractions, we will have a polynomial in numerator degree higher than polynomial of denominator. This calls for long division. Today we'll review why we do long division and how exactly to do that in case of a polynomials. Recall that we know how to convert an improper number to the mixed integer. For example, we have 295 divided by 14. This is an improper number because 295 is clearly larger than 14. Doing long divisions, we can simplify or rewrite this fraction as a quotient plus a remainder that is smaller than the divisor. Doing the long division means figuring out how many times 14 will fit into 295. Clearly 14 would fit twice in the 29. Let's subtract from 29 28. We will get 1. Carrying over 5 takes us to the second iteration of a long division. And now we ask the same question, how many times 14 will fit into 15? Since it fits only once, we now know the answer to our question. We can see that 14 fits 21 times into 295, leaving 1 as a remainder. We'll continue this process of long division until the number that remains from the division is strictly smaller than 14 we're trying to divide by. Rewriting an improper number 295 divided by 14 as a mixed integer means representing it as an integer number 21 plus a remainder 1 over 14. This is the same process we're going to repeat when dividing one polynomial by another polynomial. When we have a rational function, polynomial divided by polynomial, and a polynomial written in numerator has a degree same or higher than a polynomial written in denominator, we can do exactly the same procedure, long division, and rewrite an expression as a quotient plus remainder over the divisor. Let's consider an example, 3x cubed minus x squared plus 4x plus 5 divided by x squared plus 3. Our dividend, 3x cubed minus x squared plus 4x plus 5, has every term present in the polynomial. We have x cubed multiplied by constant 3, there is x squared multiplied by constant minus 1, x to the power 1 is multiplied by 4, and 5 is multiplied by x to the power of 0. We divide it by a polynomial of degree 2, x squared plus 3, but x squared plus 3 doesn't have obviously all terms presented. X squared is multiplied by 1, but x to the power 1 is multiplied by 0, which is sort of make its term invisible. And then 3 is multiplied by x to the power of 0. Let's write out both dividend and divisor, indicating all terms, including the ones that we're not seeing because x is multiplied by 0. And now we're going to do the same idea as before. We'll try to multiply x squared by something that will make a product equal to 3x cubed. If we'll take 3x and multiply it by x squared, we will have exactly 3x cubed. But 3x will also be multiplied by 0 times x, creating 0 times x squared. And 3x multiplied by 3 is equal to 9x. Just as before, we will subtract from the first line our second line term by term. 3x cubed will be cancelled with 3x cubed. Minus x squared minus 0x squared is minus x squared. 4x minus 9x is minus 5x. We will carry over 5. Now this is a second iteration of a long division. Let's determine what we can multiply x squared by to create minus x squared. It should be negative 1. Minus 1 times x squared is exactly negative x squared. Minus 1 times 0x is 0x. Minus 1 times 3 is negative 3. Now let's subtract our last row from the row above. Minus x squared is 0. Minus 5x minus 0x is minus 5x. 5 minus minus 3 is 5 plus 3, or 8. Completing long division allowed us to determine the whole part. 3x minus 1, we call this quotient. Therefore, our rational function can be written as 3x minus 1 plus a fraction where in numerator we have a remainder minus 5x plus 8, and in denominator is our original divisor, x squared plus 3. And this is all there is to the procedure of dividing polynomial by polynomial. I hope you found it useful. See you next time.